In the endless blackness of the cosmos, where light travels for millions of years before finding another eye to witness it, something extraordinary has happened. On October 29th, a silent traveler from the depths of interstellar space approached the heart of our solar system. For months, astronomers had been tracking its journey, expecting a predictable encounter, a cometary passage that would fade into the archives of observation. Yet as the object known as Three-Eye Atlas swept past the burning brilliance of our star, reality itself seemed to shift. Its motion, its light, even its very behavior began to whisper of something that should not be possible. At first glance, the news appeared simple enough. A body passing through perihelion, the closest point to the Sun. But when the Atacama Large Millimeter Array, the ALMA telescope, captured its precise position, the data told a story that defied ordinary physics. The object was not where it should have been. It had deviated by 4 arc-seconds from its calculated trajectory. To the untrained eye, that number may seem negligible, a flicker on the screen. Yet in the precise geometry of the heavens, 4 arc-seconds is a chasm, an invisible force bending the expected into the unknown. Astronomers call it non-gravitational acceleration, a term that sounds sterile, almost technical, until one realizes what it implies. Something was pushing the object besides the pull of our sun. No jet of escaping ice or gas could be measured, no plume of material drifting into space. A comet can accelerate as frozen volatiles evaporate and act as miniature thrusters, but in this case there was silence. No tail large enough, no mass loss visible. The laws we rely on to describe the heavens seemed to hesitate. And then came the light. The solar observatory. So recorded Atlas becoming brighter than ever before, shining with a deep electric blue, a hue more intense than the sun itself. This was the 9th anomaly linked to the object, and yet it was not the final one. The color shift suggested scattering processes far beyond the known behavior of cometary dust. The surface appeared to interact with light in a way that no natural body should. Was it composition, temperature, or something else entirely? The community of astronomers and physicists felt the tremor of possibility. In the language of data and error margins, excitement grew. If this acceleration were real and persistent, Atlas would have to shed at least 15% of its mass, more than 5 billion tons of material, leaving behind an immense cloud of debris. Such a cloud would have been visible in every spectrum we use to observe the sky. Yet it was not. Now, as the calendar moves toward December 19th, 2025, the countdown has begun. The object will pass near Earth, close enough to be studied in exquisite detail. The question that grips the scientific world is deceptively simple. Will we see the cloud of debris that should exist if conventional physics holds true? Or will we find a 10th anomaly, a body that accelerates without losing mass, a phenomenon that slips through the fingers of known science? To understand what this means, we must remember that Atlas is not just another comet. It is the 3rd confirmed interstellar visitor ever detected, after the enigmatic 1I Oumuamua in 2017 and the Comet 2, I Borisov in 2019. But even among such rare company, Atlas stands apart. It is larger, faster, stranger, a statistical impossibility that forces us to look again at the quiet assumptions we make about the universe. The first signs of its peculiarity emerged in its orbit, a retrograde path almost perfectly aligned with the plane of the solar ecliptic. The odds of such precision occurring by chance are barely 0.2%. The second anomaly was even more unsettling, an anti-tail directed toward the sun itself, defying the standard behavior of cometary material pushed outward by solar radiation. Instead of retreating, Atlas appeared to reach toward our star, as if pulled by an unseen design. One by one, 9 anomalies have accumulated. each challenging another principle of natural celestial mechanics. And now, with the discovery of non-gravitational acceleration unaccompanied by mass loss, the mystery deepens to an almost mythic degree. What kind of body behaves as if propelled by an internal force, yet shows no evidence of outgassing or fragmentation? What substance could reflect light in a blue more vivid than our own sun, while remaining intact against its immense heat? Perhaps most haunting of all is the direction from which Atlas came, a trajectory intersecting, within mere degrees, the origin of the legendary WOW signal detected in 1977. Coincidence, say some. A resonance in history, say others. Whatever the truth, the echoes of that mystery seem to return with every observation. The days following the October passage have left scientists both exhilarated and unsettled. In observatories across the world, instruments continue to track the faint shimmer of Atlas as it moves outward again, carrying with it the secrets of its impossible journey. Its blue light has become a question written across the dark. What if this is not a comet at all? What if, for the first time in human history, we are watching something designed, something sent? And yet, we must remain cautious. Science demands patience, evidence, replication. It is too early for conclusions, too dangerous for assumptions. But in the stillness of the cosmic night, even the most disciplined mind cannot help but wonder. December 19th will bring the next chapter. Until then, every telescope on Earth and beyond is turned toward a single point of light that refuses to behave as it should. Something is moving in the heavens, and it is unlike anything we have ever seen. When the object designated 3I Atlas first appeared in the outer regions of the solar system, few suspected that it would become one of the most puzzling and transformative discoveries in modern astronomy. Its discovery was not a chance event, but the result of a global collaboration among observatories and space agencies. The Pan-STARRS survey in Hawaii first detected its unusual trajectory, while subsequent observations by the European Southern Observatory, the Hubble Space Telescope, and the Atacama Large Millimeter Array revealed patterns that contradicted established celestial models. Each new dataset deepened the enigma. From the very beginning, Atlas challenged statistical expectation. Its incoming velocity, exceeding 62 kilometers per second, indicated an origin outside our solar system, yet its trajectory aligned almost perfectly with the plane of planetary motion. Such alignment should have been astronomically rare. Natural interstellar visitors usually approach from random inclinations, their paths determined by the gravitational chaos of the galaxy. But Atlas moved as if it had aimed precisely for our solar plane, following a route that maximized observation opportunities from Earth. For many scientists, that was coincidence. For others, it was the first whisper that something extraordinary might be unfolding. Spectroscopic analysis soon followed. The Very Large Telescope in Chile and NASA's Infrared Telescope facility in Hawaii began to dissect the light coming from the object. The results were immediately perplexing. The ratio of nickel to iron in its spectrum did not resemble that of any known cometary or asteroid population. Instead, it mirrored metallic compositions produced only under extreme conditions: high-energy melting, alloy formation, processes that on Earth occur in industrial furnaces or the cores of differentiated planets. Even more confounding was the absence of key volatile compounds: water vapor, carbon dioxide, and ammonia, the lifeblood of cometary activity, were nearly missing. The data showed only 4% water content by mass. For a so-called comet, it was an almost barren, rocky worldlet. Then came the strange glow. Around the time of its perihelion passage on October 29th, the Solar and Heliospheric Observatory recorded a surge in luminosity by a factor of 7. The object became a radiant blue, its light scattering in a wavelength region shorter than any known cometary emission. Normally, such brightness correlates with violent sublimation, the shedding of tons of gas and dust. yet the coma around Atlas remained inexplicably thin. The photometric models indicated a surface capable of reflecting light more efficiently than ice or silicate dust, almost as if coated in a microstructured material that manipulated light at the nanoscale. The implications of this blue shift rippled through the scientific community. Was it a new kind of matter? Could cosmic radiation have altered its surface to create exotic reflective compounds? Or was it a clue that Atlas was something engineered, a possibility that few dared to articulate publicly? Theoretical astrophysicist Avi Loeb of Harvard University did not shy away from the question. He proposed that the acceleration, the unusual light curve, and the precise alignment of its orbit warranted an open-minded approach. Perhaps, he suggested, we were observing the product of technology rather than geology. His stance drew criticism, but also curiosity. After all, Loeb had once raised similar questions about Oumuamua, the first interstellar visitor ever detected. But before imagination could outrun evidence, data began to accumulate from ALMA and from the Solar Dynamics Observatory. The measurements confirmed a non-gravitational acceleration. In practical terms, Atlas was speeding up as it departed the Sun's influence, not slowing down as gravity would dictate. This was not a subtle drift. It was measurable and repeatable. Yet no jets of vapor were detected, and no plume of debris surrounded it. The calculations were sobering. If the acceleration had been caused by conventional outgassing, the object would have had to lose roughly 5 billion tons of material, 15% of its total estimated mass, but telescopes found nothing. The vacuum around it was clean. To astronomers trained to interpret celestial behavior through physics alone, such a finding bordered on heresy. Nature, they argued, does not cheat its own equations. Something was applying a force. Radiation pressure from sunlight was considered but quickly ruled out. For the pressure of photons to produce that acceleration, the object's surface would need to be astonishingly thin, no thicker than a millimeter, and spread over hundreds of meters like a solar sail. That image alone sent tremors through the astrophysical community. Could it be that Atlas was not a solid rock at all, but a vast, ultralight structure drifting between the stars? Meanwhile, other anomalies demanded attention. During the months preceding perihelion, solar coronagraphs observed a faint jet of material directed toward the Sun rather than away from it. It was the inverse of normal cometary behavior, a phenomenon dubbed the antitail. This reversed outflow contradicted both radiation dynamics and thermal models. Some speculated that magnetic forces might be at play, perhaps a reactive magnetic field induced by metallic components interacting with solar plasma. Others argued it might be a mere optical illusion caused by viewing geometry. But the models disagreed. The jet remained stable for nearly 2 weeks, indicating a sustained, deliberate pattern. In August 2025, as the object crossed the orbital distance of Venus, its brightness oscillated rhythmically, increasing and fading in intervals of roughly 43 minutes. Such periodic fluctuations suggested rotation, but the timing did not fit any simple spin model. The light curve displayed complex harmonics, as though different regions of the object alternated between reflection and shadow, almost like panels moving in sequence. Some researchers even proposed the possibility of controlled orientation, an adjustment in angle relative to solar radiation. For those watching, it felt as though the object were responding, adjusting, maneuvering. By the time Atlas reached perihelion, every major space agency had redirected part of its observational capacity toward it. NASA coordinated with the European Space Agency and the Japanese Aerospace Exploration Agency to schedule a chain of simultaneous observations across multiple wavelengths. The ALMA array focused on millimeter emissions to detect thermal gradients. The Hubble telescope monitored optical variation. The James Webb Space Telescope, with its infrared sensitivity, scanned for signatures of complex molecules, yet the outcome only thickened the mystery. No organic compounds typical of cometary material were found. Instead, Webb detected sharp spectral lines corresponding to highly ionized nickel and chromium, elements associated with processed alloys. Parallel to these efforts, ground-based radar from Arecibo's successor facility attempted to bounce signals off the object. Only a faint echo returned, weaker than expected for an object of its estimated mass and size. The radar cross-section suggested an irregular, possibly hollow form, a structure whose internal density was far below that of rock. When modeled, the shape best matched a broad, thin ellipsoid, somewhat like a flattened disk. That geometry alone could explain the low reflectivity and peculiar light curve, but it also evoked comparisons with the hypothesized concept of interstellar light sails, theoretical probes propelled by starlight. Throughout all of this, skepticism remained the rule. Extraordinary claims, as Carl Sagan once reminded us, require extraordinary evidence. Many scientists warned against anthropocentric bias, the human tendency to see intention where there is none. They argued that unknown natural processes might be responsible, sublimation of exotic ices, electrostatic forces, or fragmentation events yet to be detected. The debate grew into one of the most intense scientific discussions of the decade, with papers, preprints, and counterarguments flooding astrophysical journals almost weekly. Still, the numbers refused to conform. The cumulative probability that all 9 anomalies, trajectory, anti-tail, composition, lack of volatiles, negative polarization, brightness oscillation, non-gravitational acceleration, metallic ratio, and approach direction, could occur naturally was less than 1 in a million. The statistics did not lie. The universe, vast as it is, rarely orchestrates coincidences on that scale. Avi Loeb's group proposed a new observational campaign to exploit the Sun's gravitational lensing effect. As Atlas passed behind the solar disk from our vantage point, the Sun's gravity would bend its light, allowing scientists to measure tiny deviations, mere fractions of an arcsecond, that could reveal internal structure. The predicted deflection was 0.27 arcseconds, a subtle but measurable distortion. If detected, it might uncover whether the object was opaque, hollow, or perhaps even surrounded by an artificial field. Preparations for this experiment became one of the most ambitious coordination efforts among observatories ever attempted. Meanwhile, other astrophysicists turned to simulation. Supercomputers at the Max Planck Institute for Astronomy modeled every possible combination of physical parameters: composition, shape, spin, reflectivity, radiation pressure, to reproduce the observed data. No natural configuration fully matched the results. Some models came close by invoking layered ice-metal composites or frozen gas pockets that vented asymmetrically, but none accounted simultaneously for the color, acceleration, and lack of debris. As the year progressed toward its final months, the focus shifted to December 19, 2025, the date of Atlas's closest approach to Earth. During that brief window, every major telescope on the planet would point toward the interstellar traveler. If the object had truly lost 5 billion tons of mass, a colossal cloud of dust should precede it, easily visible to even amateur astronomers. If no such cloud appeared, it would confirm the existence of the 10th anomaly: propulsion without material loss. In anticipation, the scientific community held its breath. For all its equations and caution, astronomy has always carried a pulse of wonder, the same curiosity that once drove Galileo to aim his telescope at Jupiter's moons. The difference now is that the mystery no longer lies within our solar system, but beyond it, in an object that seems to straddle the line between nature and technology. As the last pre-encounter observations came in, a realization began to form. Regardless of the final explanation, 3i Atlas had already achieved something unprecedented. It had united the scientific world in a shared pursuit of truth, forcing humanity to look outward with renewed humility. Whether an alien artifact, a cosmic anomaly, or a natural wonder we have yet to comprehend, Atlas had become a mirror for our curiosity, a question suspended between the stars, daring us to look closer. The night skies of early December shimmer with anticipation. Instruments are calibrated, coordinates aligned, data pipelines synchronized. Somewhere, high above the noise of the atmosphere, an interstellar traveler moves silently toward us. It is indifferent to our excitement, untouched by our theories, and yet, in its wake, it leaves the tremor of something profound, the sense that we are standing on the edge of a revelation that could redefine our understanding of the universe itself. Long before Atlas crossed the invisible border into our solar system, before its name appeared in observatory logs and scientific bulletins, it had already been wandering through the dark for perhaps millions of years. Interstellar objects are time capsules of creation, fragments born in the violent birth throes of stars, thrown into the endless night, drifting between galaxies. But Atlas, unlike those ancient castaways, carries an aura of intent. Every observation, every measurement has painted the picture of something that does not simply drift, but seems to travel with purpose. To understand its full significance, we must look not only at the data, but at the people who have devoted their lives to deciphering it. Among them stands Professor Avilob, whose calm voice and patient reasoning have often cut through waves of skepticism and controversy. A theoretician by training, Loeb has spent decades exploring the cosmic frontier, where mathematics meets imagination. His approach is simple yet radical. When evidence challenges theory, theory must bend. His earlier work on Oumuamua prepared him for the questions now raised by Atlas. In lecture halls and interviews, he has repeated a single refrain, that science advances only when we dare to consider what others find unthinkable. His stance has not been without cost. Many in the field of astrophysics have urged caution, accusing him of speculation. Yet Loeb remains undeterred. To him, Atlas is not proof of alien technology, but a test of scientific courage, a reminder that the universe is not obliged to fit within the comfort of human expectation. In his Harvard office, surrounded by equations scrolled across whiteboards, he often speaks of humility, that the vastness of the cosmos demands an openness of mind equal to its scale. For Loeb, whether Atlas is natural or artificial, it forces humanity to confront its place in a universe that may be far more complex and far more alive than we once imagined. The instrument that first revealed the anomalous acceleration, ALMA, stands on a high Chilean plateau, where the air is so thin that even breathing feels like an act of endurance. It is here, beneath the cold glow of southern stars, that human ingenuity meets the ancient silence of space. Each of ALMA's 66 antennas gathers invisible waves of millimeter radiation, stitching them into images of distant worlds. When the faint signal from Atlas arrived, no one in the control room fully grasped its importance. The deviation seemed minor, a statistical curiosity. Yet within hours, computers confirmed what would become one of the defining moments in observational astronomy, a non-gravitational acceleration without measurable mass loss. From that point on, the story of Atlas left the pages of technical reports and entered the realm of scientific legend. The history of such discoveries is a tapestry woven with persistence and doubt. When Galileo first turned his telescope to the heavens, he saw moons orbiting Jupiter, a sight that contradicted centuries of belief. When Einstein proposed that gravity could bend light, many dismissed it as mathematical fantasy until the solar eclipse of 1919 proved him right. Atlas now stands at a similar threshold. If it obeys laws we have yet to discover, it could reshape astrophysics as profoundly as those earlier revolutions. For engineers and astronomers, their fascination lies also in its physical form. The radar echoes, suggesting a hollow or thin structure, ignite visions of technology far beyond our own. Could it be that somewhere, in a distant star system, an ancient civilization mastered the art of interstellar travel, sending forth autonomous sails to map the galaxy? Or is Atlas merely a fragment of an exotic planetary crust, flung into the cosmos by forces beyond comprehension? Both possibilities stretch imagination to its limits. The object's sheer endurance is itself a mystery. To survive the journey through interstellar space, the radiation, the collisions with micrometeoroids, the gravitational tides of passing stars, requires extraordinary resilience. Whether forged by nature or design, Atlas has endured what no fragile construct should. Its surface, according to infrared data, is coated with compounds that resist vaporization even under intense solar heat. If natural, it might represent a new class of interstellar material, a bridge between rock and metal, born in the remnants of a supernova. If artificial, it could be evidence of engineering that has long outlived its makers. As the date of its closest approach draws near, excitement builds not only in laboratories, but in the hearts of those who watch the sky simply for wonder's sake. Amateur astronomers across continents prepare their telescopes, hoping to catch a glimpse of the traveler whose story has captivated the world. The data they gather will join the great network of observation stretching from mountain summits to orbital observatories. Every spectrum, every photon recorded will bring us closer to the truth, or deepen the mystery further. In this pursuit, there is something profoundly human. We are a species that has always looked upward, seeking patterns in the stars, finding meaning in the infinite. Atlas reminds us that the universe is still capable of surprising us, still capable of humbling us. Its strange blue glow, visible even to modest instruments, has already entered the shared imagination of humanity, a symbol of the unknown that waits just beyond the limits of understanding. Whatever the final verdict may be, the discovery of Atlas has already achieved something remarkable. It has united scientists, engineers, and dreamers under a single question. What is moving out there, and why? For a brief moment, the divisions between disciplines and nations fade, replaced by the collective thrill of curiosity. Conferences once bound by routine now open with discussions about propulsion without mass loss, metallic reflectivity, and interstellar trajectories. New models of non-gravitational dynamics are being written, new instruments proposed. The very boundaries of astrophysics are stretching. The future of this investigation may depend on the upcoming gravitational lensing experiments, which will use the sun's curved space-time as a cosmic magnifier. If those observations reveal asymmetries or unexpected diffraction patterns, we may finally glimpse the true structure of Atlas. If not, the mystery will remain unsolved, preserved in data for generations to come. Either way, it will leave a legacy. Future explorers, perhaps centuries from now, may look back on this moment as the dawn of a new era. The moment humanity realized that the cosmos contains phenomena beyond natural precedent. It is possible that December 19th will arrive and the telescopes will see nothing unusual. No debris, no glow, just a silent traveler fading into the dark. It is equally possible that the night will ignite with revelation. A cloud may appear, confirming outgassing, or the acceleration may continue without explanation, demanding theories we have not yet written. The outcome does not diminish the wonder. What matters is that we are watching, measuring, learning. In the end, Atlas is more than an astronomical object. It is a mirror reflecting our deepest impulses, our hunger to understand, to explore, to connect with something greater than ourselves. Whether it proves to be a natural wanderer or a messenger from another intelligence, it has already changed us. It has reignited the spirit of discovery that once propelled humanity beyond the limits of its own planet. As the object recedes into the distant night after its encounter, its faint blue shimmer will linger in our instruments and our memory. It will remind us that the universe is vast, not only in scale, but in possibility. Somewhere out there, beyond the reach of our telescopes, other travelers may be drifting, silent, ancient, enigmatic, carrying the stories of worlds unknown. Atlas, whatever its nature, has opened a doorway of imagination through which science must now step. And perhaps, as we continue to search the skies, we will realize that the greatest discovery is not the object itself, but the renewed courage to wonder